Today we will explore how scientists can map the Higgs potential and reveal the phase diagram of our very universe using larger, more powerful particle colliders. This is a vital pursuit that will reveal how the universe has evolved and how it may end.
I have no memory of this place.
Charting the evolution of the Higgs potential and the changing Higgs field strength in the vacuum of our universe since its creation is one of the most important pillars of the physics programs planned for new, more powerful particle colliders. Mapping the changing Higgs potential will allow particle physicists to gain an insight into exactly how and why fundamental particles acquired their mass, how our universe has evolved, and how it may come to a cataclysmic end. If you would like to review the nature of the Higgs potential and the evolution of the Higgs field within the framework of the Standard Model, review episode number 2. If you would like to understand why charting the evolution of the Higgs potential is so important, review episode 3. Today, we ask 2 simple questions. 1. How can physicists map the true evolution of the Higgs field throughout the history of our universe? And 2. Why does such a mapping demand the funding, building, and operation of larger, more powerful particle colliders? However, before we can answer those crucial questions, a very rapid review of the Higgs potential and electroweak symmetry breaking. Skip to the timestamp on screen if you're familiar with that material or have reviewed episodes 2 and 3. According to quantum field theory, the vacuum of our universe is not really empty, but rather a boiling sea of quantum fields associated with every fundamental particle we know and do not yet know. One of those quantum fields is the Higgs field. All of these fields have an associated potential, which depends on the strength of the field in the vacuum. Usually the potential energy distribution of quantum fields takes a parabolic shape, and these fields, although oscillating, take an average value of 0, the value of the field that minimizes the potential energy. Systems like to sit at energy minima. We can excite fundamental particles out of the fields by pumping energy into them, like we do at particle colliders, but on average, these fields are turned off. The Higgs potential is the Higgs field's vacuum energy density, the energy density stored in the omnipresent Higgs field, the Higgs field's contribution to the energy density of empty space. The Higgs potential is dependent on the strength of the Higgs field in the vacuum of our universe. According to the Standard Model, a 4-component Higgs field existed in the very earliest moments of the universe. At this point, the universe was incredibly hot and dense, and the Higgs potential took a typical parabolic form. The vacuum of our universe sat at the minimum of the potential, the origin, and all the components of the Higgs field took an average value of 0. Fundamental particles therefore were massless and whizzed around the early universe at the speed of light. However, after around 10 to the minus 11 seconds, as the universe expanded and cooled, its temperature dropped below a critical temperature, and the shape of the Higgs potential morphed from parabolic into the wine bottle or Mexican hat-shaped classical Standard Model Higgs potential, typically presented in particle physics outreach materials. The Higgs potential developed a ring of new, lower energy ground states, and the vacuum of our universe naturally rolled from the origin down the potential hill and into one of those lower energy ground states, much like a ball rolling down a smooth hill. This process imbued the weak bosons, the W+, W-, and Z, with mass, a phenomenon known as electroweak symmetry breaking, and also powered up the scalar Higgs field. This produced a constantly switched on quantum treacle everywhere in our universe. Fundamental fermions began to ping off this field and also acquired their mass. As such, the changing form of the Higgs potential solves a number of deep problems in particle physics and provides the simplest and crudest explanation for how fundamental particles, excluding neutrinos, acquire their mass. However, there is a massive, gaping hole in our picture of how fundamental particles acquire their mass. Despite the importance of the Higgs potential in explaining the evolution and current state of our universe, and despite the ubiquity of the infamous classical Standard Model Higgs Mexican hat potential in popular physics media, the true shape of the Higgs potential has never been experimentally validated. The form of the Higgs potential in the Standard Model is the simplest and crudest that gets the job done. The bare bones form of the potential that ensures that the weak bosons and fundamental fermions are massive in our modern universe. However, there are many different ways to roll down a potential hill and produce a universe full of massive particles. As such, there are many competing theoretical shapes of the Higgs potential. Each of these forms is associated with a radically different evolution of our universe and the existence of radically different beyond Standard Model physics. Physics that could tell us how the universe evolved, why we are here, and where the universe is heading. Just as particle physicists assumed the Higgs boson existed for the more than 50-year span between Higgs's seminal papers and its discovery at the Large Hadron Collider in 2012, physicists are still assuming that our Standard Model picture of electroweak symmetry breaking is correct and complete. But what if it isn't? It's very possible that our Standard Model picture of electroweak symmetry breaking and the evolution of the Higgs potential is wrong. We cannot assume that the classical Standard Model form of the Higgs potential is the true form of the Higgs potential in our universe. We need to map that true shape. Part of the potential of new, more powerful particle colliders is nailing the Higgs potential. So it's clear that mapping the true, evolving form of the Higgs potential in our universe is a key goal for particle physicists. But how can that goal be achieved? The Higgs potential is the Higgs field's contribution to the energy of empty space. It varies as the strength of the Higgs field in the very vacuum of our universe varies. But how can we possibly map such a distribution? It's not like we can dial the Higgs field strength throughout our universe up and down and measure the changing energy density within the vacuum. What's more, the Higgs potential depends on the temperature of the universe, and as such, the strength of the Higgs field has varied as the universe has expanded and cooled. How can we map those changes? Experimental particle physicists are stuck at one point in time, one temperature, T = 0 today, and one Higgs field value, the current vacuum expectation value. We're trapped at one position, a minimum of the Higgs potential. In order to understand how the shape of the Higgs potential changed with the cooling of our universe, we need to understand the current shape of the Higgs potential extremely precisely. Then theorists can perform what is known as thermal quantum field theory. They can calculate how the Higgs potential of our field would look if the temperature of the universe were raised. Taking these calculations and well-established models of how the temperature of the universe has changed during its expansion, theorists can then confidently predict how the Higgs potential must have looked at various stages in the past, how it has evolved, and the electroweak phase diagram of our universe. They can test the picture of the electroweak phase transition predicted by the Standard Model. So that takes care of the temperature changes. However, that still leaves us needing to understand the current shape of the Higgs potential at the current temperature of our universe. How on earth can we do that? The key is the Higgs boson. The window through which we interact with the Higgs field pervading our universe is its excitation, the infamous Higgs boson. Mapping the Higgs potential will require us to interrogate the Higgs boson and its interactions. However, it turns out that our measurements of the Higgs boson to date can't help us very much. Despite our discovery of the Higgs boson in 2012 and a decade of subsequent study, our knowledge of the Higgs boson tells us very little about the shape of the Higgs potential. As we saw in episode 2, the classical Higgs potential predicted by the Standard Model depends on only two parameters, mu squared, the mass squared parameter, and lambda, the Higgs self-coupling parameter. The values of these parameters are not predicted by the Standard Model theory. They are related to the mass of the Higgs boson and the well-known strength of the Fermi constant from electroweak theory. Notice that the Standard Model does not predict the mass of the Higgs boson from first principles. It was discovered by experiment in 2012. This allowed the mass squared and self-coupling parameters to be calculated and the shape of the classical Standard Model Higgs potential predicted in our modern universe to be determined. With these values in hand, the shape of the Standard Model Higgs potential and the Standard Model Higgs mechanism can predict the mass of the W boson and Z boson, and these predictions prove to be in excellent agreement with experiment. The Higgs mechanism also predicts that fundamental fermions, quarks and leptons, should couple to the Higgs boson with a strength that is proportional to their mass. Measurements of these couplings made over the last decade for the heaviest fundamental fermions have been consistent with that prediction. So, over the past decade, since the discovery of the Higgs boson, we have successfully verified that the standard model Higgs mechanism, which rests on the classical Higgs potential, is consistent with experimental data. It seems to give appropriate masses to the gauge bosons and fundamental fermions, and results in a powered up Higgs field throughout our universe, whose existence is betrayed by its excitation, the Higgs boson. However, despite all this phenomenal progress, we have done very little to verify that the form of the standard model classical Higgs potential is accurate, and the correct choice amongst many viable candidates. So how can we map the true shape of the Higgs potential in our universe? It turns out that to map the Higgs potential, we have to play a mathematical trick, a trick undergraduate physicists will be well versed in. We know our current vacuum must sit at a minimum of the Higgs potential, as that's where systems naturally roll and come to rest. At this minimum, we can treat the Higgs field as a field with a constant background vacuum expectation value plus a fluctuation, its excitation, the Higgs boson. And we can expand the potential mathematically around the minimum. When we perform this procedure, we find that the shape of the Higgs potential around its current minimum is dependent on a series of terms in rising powers of the Higgs. The first term is quadratic in the Higgs and tells us the mass of the Higgs boson as a function of the vacuum expectation value and Higgs self-coupling parameters. This makes perfect sense. The Higgs mass is determined by how quickly the energy of empty space changes as you vary the Higgs field's value away from where it prefers to be, the vacuum expectation value. A Higgs boson is a little ripple in the Higgs field, i.e., as a Higgs particle passes by, the Higgs field has to change a little bit, becoming in turn a little bit larger and a little bit smaller. Any small change in the Higgs field value slightly increases the energy of the vacuum overall, the Higgs potential. This extra bit of energy gives the Higgs particle part of its mass energy, its E equals mc squared energy. As such, it turns out that the mass of the Higgs boson is related to the curvature, the flatness or sharpness, of the Higgs potential around its expectation value. So, in finding the Higgs boson in 2012 and measuring its mass of 125 GeV, we only measured the curvature of the Higgs potential in the immediate vicinity of the current vacuum expectation value. As such, we know our universal vacuum must currently sit at a minimum of the Higgs potential, and we know from measuring the Higgs mass that the potential is roughly parabolic around that vacuum expectation value. But that's pretty much all we do know. Just as particle physicists assumed that the Higgs mechanism worked and the Higgs boson existed for almost 60 years, now particle physicists are working under the assumption that the standard model Higgs potential is accurate, and that potential takes the crudest, smooth form that gets the job done. So how can we go further and map the true Higgs potential far away from our minimum? Well, what we need to do is determine more, higher order terms in the expansion of the Higgs potential about the minimum. If we can very carefully map the shape of the potential around our current vacuum position, we can project those shapes to higher and lower field values and begin to understand the true, wider shape of the Higgs potential. Notice that those higher order terms are cubic and quartic in the Higgs. This means that they depend on the strength of simultaneous interaction between 3, 4, or even more Higgs bosons, the self-interactions of the Higgs boson. That means that the standard model predicts the existence of new, never before observed interactions where 3, 4, or even more Higgs bosons interact simultaneously. The realization we come to is that although we cannot map the Higgs potential directly by varying the Higgs field strength of our universal vacuum, we can map it around our current minimum by smashing particles together at incredibly high energies, exciting not one but multiple Higgs bosons out of the Higgs field, and then observing how they bash off one another. In order to study these triple Higgs and quartic Higgs interactions, we look to create collisions that produce 2 Higgs bosons in the final state, but which proceed via a triple or quartic Higgs interaction. These are so-called di-Higgs events, double Higgs events. The standard model insists that the rate at which these di-Higgs events should be produced in high-energy particle collisions at a machine like the LHC depends on the self-coupling term in the classical Higgs potential and the vacuum expectation value of the Higgs field in the vacuum of our universe. The standard model values of these quantities were fully determined when the mass of the Higgs boson was found to be 125 GeV in 2012. As such, since 2012 we have had the ability to predict how often 3 and 4 Higgs boson self-interactions should occur following high-energy particle collisions in a machine like the Large Hadron Collider. So, if we can measure the true rate at which di-Higgs events occur in high-energy particle collisions, we can tease out the true value of the Higgs self-coupling constant in our universe, and we can map the true Higgs potential of our universe. If these interactions occur more frequently or less frequently than the standard model predicts, the Higgs self-coupling constant and the shape of the Higgs potential in our universe must differ from the classical standard model predictions. These divergences would be an instant indication that new, beyond standard model physics is at play in the Higgs sector. A potential deviation of the measured Higgs self-coupling term from the standard model prediction is typically quantified in a value known as kappa lambda, the ratio between the measured value of the Higgs self-coupling strength and the standard model prediction. Hence, kappa lambda values greater than 1 indicate that the true Higgs self-coupling value in the universe is higher, and di-Higgs events occur more often than the standard model predicts. On the flip side, kappa lambda values less than 1 indicate that the true Higgs self-coupling value of the universe is lower, and di-Higgs events occur less often than the standard model predicts. Specific, beyond standard model physics hypotheses predict specific patterns of deviations in the rates of di-Higgs events, specific kappa lambda values, and hence specific changes to the shape of the Higgs potential relative to standard model predictions. So by measuring the rates of di-Higgs events, we may be able to focus on where new physics is hiding. The bottom line is that by measuring the rate at which di-Higgs events occur, physicists should be able to map the higher moments of curvature of the Higgs potential around the vacuum expectation value and make important inferences about the shape of the Higgs potential. We're standing in a valley, but it seems we do have pathways to peak out. We have pathways to nailing the shape of the Higgs potential and how it has changed throughout the evolution of our universe. Okay, but if mapping the Higgs potential is so incredibly important and could shed light on so many fundamental questions, and we know how to start mapping it, why haven't we done it already? Well, as we just saw, mapping the Higgs potential requires us to study the self-interactions of 3, 4, or even more Higgs bosons, and producing the required di-Higgs events at a collider like the currently operational LHC is incredibly challenging. The following Feynman diagrams show two of the principal ways in which di-Higgs boson events are produced at the LHC. Both require gluon fusion. In both cases, two gluons from colliding protons interact, and in both cases, two Higgs bosons are produced in the final state. The first Feynman diagram produces two Higgs bosons in the final state, but does not contain a triple Higgs coupling, and is uninteresting when looking to study the Higgs potential. However, in the second Feynman diagram, we see the triple Higgs interaction. One virtual Higgs boson is produced and decays into two real Higgs bosons. 3 Higgs bosons meet at a single point. These are the events we want to produce, so that we can determine their rate, tease out the triple Higgs interaction strength, and calculate the third moment of the shape of the Higgs potential. However, at the LHC, we have a quantum mechanical problem. Since these two processes have the same initial and final state, and similar probabilities of occurring, they interact very strongly, and it turns out with opposite signs. That means that these two processes interfere destructively, and almost entirely cancel one another out. As such, the production of useful di-Higgs final states is incredibly suppressed at the LHC. In addition, Higgs bosons are heavy, 125 GeV each, hundreds of times heavier than the proton. As such, a significant fraction of the collision energy of the colliding protons is needed to create two Higgs bosons in the final state, and di-Higgs production rates are reduced relative to single Higgs production rates. At the LHC, the production of one Higgs boson is already a rare process. Only roughly 1 in every billion proton collisions produces a Higgs boson. Events in which two Higgs bosons are produced, di-Higgs events, are expected to be incredibly rare, 1,000 times more rare than the infrequent production of a single Higgs boson. In fact, di-Higgs events are so rare that during Run 2 of the LHC between 2015 and 2018, the Standard Model predicts that only 4,000 di-Higgs events were expected to have occurred, compared to the 40 million collisions that happen during every second of the machine's operation. Attempting to capture di-Higgs events is like going after the needle in the proverbial haystack. Capturing and recording these incredibly rare di-Higgs events when they do occur is also incredibly challenging. The two Higgs bosons in the final state do not hang around very long and rapidly decay. As such, we only see the debris that the Higgs bosons fall apart into in our detectors, and we have to reconstruct and infer that a di-Higgs event occurred by combining the energy and momentum of these final state particles that smashed into our detectors. The needle in a haystack we're looking for is really an invisible type of needle that rapidly changes into other types of needles. So how can we capture as many di-Higgs events as possible when the Higgs bosons disintegrate so quickly? Well, Higgs bosons couple more strongly to more massive particles, and hence decay most frequently to messy bottom quark pairs. As such, you might think that the best way to capture as many di-Higgs events as possible is to look for Higgs bosons decaying to bottom quark pairs. However, there's a problem. Since quarks and antiquarks are never seen in isolation, but always confined in hadrons, quarks tend to produce messy jets of numerous secondary hadrons when they're produced by a decaying Higgs boson. Therefore, finding and reconstructing 4 bottom quark jets to find 2 Higgs bosons in a single messy event at a hadron collider is incredibly challenging, especially when there are lots of other jets of particles being produced by other background processes. As such, experimentalists often turn to less frequent decays of the Higgs, such as the decay of Higgs bosons to tau leptons or photons. Less Higgs bosons decay to these lighter particles, but these lighter particles leave much cleaner signals in our detectors, and they're easier to capture and isolate. These di-Higgs events are easier to see. As such, detecting and capturing di-Higgs events is a phenomenally precarious trade-off between frequency and signal clarity and purity. There is no golden channel, and many channels have similar sensitivity. In reality, physicists try to capture the decays of 2 Higgs bosons to numerous final states, so that they can capture as many of these precious di-Higgs events as possible. But at least 50% of those produced, according to Standard Model estimates, are simply never detected. Producing, detecting, and isolating di-Higgs events at the LHC is a painstaking, arduous, delicate, and time-consuming pursuit. Okay, so given that we can produce di-Higgs events at the LHC, what is our current measurement of the triple Higgs boson self-coupling constant, and what can it tell us about the Higgs potential of our universe? Well, that's a tricky question, because currently, given the slow rate of di-Higgs production at the Large Hadron Collider, physicists have not been able to definitively capture any di-Higgs events. However, they have been able to set stringent limits on the rate of di-Higgs production relative to the Standard Model expectation. That rate cannot be more than 3 times higher than the Standard Model expectation. Otherwise, the LHC would have already seen an unambiguous multiple sigma signal of di-Higgs production. Since the rate of di-Higgs production at the LHC is in part dependent on the coupling strength between 3 Higgs bosons, physicists have also been able to set limits on the 3 Higgs boson self-coupling parameter relative to the Standard Model expectation, and find that it falls within a region between -1.2 to 7 times the Standard Model value. Kappa lambda lies from -1.2 to 7. The strength of interaction between 3 Higgs bosons could be as much as 7 times bigger than the Standard Model predicts, and still be consistent with our current experimental data. Although these measurements are very impressive, the error bars are incredibly large, meaning that these results provide only incredibly weak constraints on the true shape of the Higgs potential. In this figure, the black line is a Standard Model prediction of the Higgs potential, but the true shape could be anywhere inside the red error ranges and still be consistent with our current experimental data. There's a hell of a lot of wiggle room. To put these constraints on the Higgs potential in context, In order to test important characteristics of the shape of the Higgs potential and key predictions made by beyond standard model physics hypotheses, our self-coupling measurements need to be accurate to roughly the percent level. Currently, we are at the 100% uncertainty level, 2 orders of magnitude short. If we want to test beyond standard model hypotheses that insist that the Higgs potential showed a first-order phase transition, hypotheses that could help to explain the matter-antimatter asymmetry of our universe, we need to reach the 1% level. If we simply want to test whether the electroweak symmetry was restored in the early universe, and that particles were massless before the electroweak phase transition, as the standard model contends, we need to measure the Higgs boson self-coupling, again with an accuracy of 1% or better. Currently, we're way off being able to tackle the key questions the Higgs potential addresses. Of course, the LHC is still running and will continue to run until the 2040s. The results we've just presented only consider data from run 2 of the LHC. New results will soon incorporate data taken during run 3. This will more than double the dataset. In addition, results from ATLAS and CMS can also be combined to roughly double the data again. In the longer term, in the next couple of years, the Large Hadron Collider will enter a long shutdown phase and will be upgraded to the High Luminosity LHC, HL-LHC. In the 2030s, the LHC will produce even more proton collision data at slightly higher energy and at an accelerated rate. Based on current projections and conservatively assuming no improvements in data analysis techniques or signal differentiation, the LHC experiments ATLAS and CMS believe that they will have a 4 sigma detection of di-Higgs production by the end of the LHC's lifetime. We will know by then whether Higgs bosons really can interact with one another, something we have never seen before. That's step number 1. However, even by the end of the LHC, we will only be able to determine the Higgs triple self-coupling to an uncertainty of around 50%. These measurements, although impressive, may not allow us to answer some of the most fundamental questions about the shape and evolution of the Higgs potential, exactly how fundamental particles acquired their mass, and whether the shape of the Higgs potential is the key to explaining the dominance of matter over antimatter in our universe. These measurements would leave us with a huge amount of uncertainty regarding the true shape and evolution of the Higgs potential of our universe. They could leave potential answers to some of the most puzzling riddles in particle physics tantalizingly out of reach. As we have seen, mapping the Higgs potential by studying the rate of di-Higgs events at the LHC is a painstaking, arduous, and Herculean task. Given this reality, we reach the inevitable realization that we will need new colliders to map the Higgs potential efficiently and to continue to seek to answer some of the most pressing open questions in particle physics. In order to drive our Higgs triple self-coupling measurements down to the 1% level and below, we could build a new, higher energy and higher luminosity proton-proton collider, essentially a larger version of the current Large Hadron Collider. Such a machine would produce a large number of di-Higgs events more quickly and allow physicists to map the shape of the Higgs potential more efficiently. One of the leading plans for a future collider is the FCC, or Future Circular Collider Program, at CERN. Physicists foresee the boring of a 100-kilometer long tunnel, 4 times the circumference of the current LHC tunnel. The first stage of the project, which could begin as early as the 2040s, would see the building of the FCC-EE collider in that tunnel. FCC-EE would collide electrons and positrons and essentially be a larger version of the Large Electron Positron Collider. FCC-EE would be a Higgs factory. Now that we know the mass of the Higgs at 125 GeV, the energies of the electron and positron beams can be carefully controlled to produce scores of Higgs bosons for experimental study. FCC-EE would run at various energies and carefully probe the couplings of the Higgs boson to other fundamental particles, take an inventory of all of its decays, and probe the electroweak scale in exquisite detail. However, it would produce essentially 0 di-Higgs events. Its energy would simply be too low. As such, it would tell us very little about the Higgs self-couplings. However, the second phase of the FCC project would be the so-called FCC-HH machine, and this is where things get interesting. The FCCEE collider would be replaced by a higher energy proton-proton collider with beam energies up to 100 TeV, an order of magnitude higher than those at the LHC. Such a machine would be capable of producing many more Higgs events than the LHC, and hence could obtain a roughly 1% level accuracy on the Higgs self-coupling over a couple of decades of operation. Such a machine will be able to carefully map the Higgs potential to high accuracy. However, there are also other options for chasing down the Higgs self-coupling. Although the experimental program of the Future Circular Collider project is deep, rich and exquisite, the FCCHH phase would not be operational until at least 2070. This leaves us with an almost 50-year gap between the present day and the operation of a collider that explores higher energies than the current LHC. Many experimentalists see this as an unacceptable situation, and one that could lead to an exodus of young researchers from the field. As such, many experimentalists, including my former colleague Patrick Koppenberg, favour the building of a linear collider at CERN, after the LHC. Such a collider would be able to smash together electrons and positrons at a range of energies, up to, and perhaps exceeding, 500 GeV. This machine's energy would be carefully tuned to produce scores of Higgs events, and provide a 10% level measurement of the triple Higgs self-coupling constant in the next couple of decades. A measurement less accurate than the FCCHH machine could boast, but available much faster. Indeed, such a machine could bridge the gap between the end of the LHC and the operation of an FCCHH-like collider at CERN, especially given that a 100 TeV proton-proton collider in a 100-kilometre long tunnel will require the development of magnet technology that does not currently exist. A high-energy muon collider, the world's first collider smashing together unstable particles, would be another option, and would even be capable of producing a sizable number of triple Higgs events and tracking down the Higgs quartic self-coupling. I don't want to lean too hard on a particular option for mapping the Higgs potential at this stage. I want to leave that for an expert discussion down the line. Suffice it to say that deciding which collider we build next is a complicated balance, taking into account timescales, geopolitics, funding, physics goals, workforces, environmental impacts, and much, much more. A new machine capable of mapping the Higgs potential with great efficiency may be a lower energy linear E plus E minus collider. It may be a larger, more powerful version of the LHC, or it might be a revolutionary new type of unstable particle smasher. The bottom line is that eventually, particle physicists will need to build a new collider to efficiently map the Higgs potential of our universe and to tackle the huge open questions that persist in particle physics. You now understand how scientists can chart the Higgs potential of our universe and determine how the Higgs field strength has changed as our universe has expanded, cooled, and evolved. You also appreciate why mapping the Higgs potential will require the building of new, expensive particle colliders. Understanding the nature of the Higgs potential will allow us to understand how the universe has evolved, why we are here, and potentially how the universe may end. It will allow us to wrestle with fundamental questions our ancestors have pondered since time immemorial. Where did we come from? Why are we here? And how will it all end? These are ultimate questions, which ultimately only particle physicists may be able to answer. However, tackling these questions will require significant funding, collaboration, foresight, and political will. We have the ability and desire to answer these questions. It's time to finalise our plans for the exciting road ahead. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.